Welcome back to another video, and in this video we are going to talk about a test that comes directly from the integral test, and it's called a p-series test, and it's actually really short and sweet and very easy to use. So let's talk a little bit about when we use it and what we need. So the p-test or the p-series test is used only when our series looks like this form. So we have to have 1 over n to some power. So for example, 1 over n squared is a p-series, 1 over n cubed. You can even have fraction exponents, 5/3 power. One of the sneaky ways that we see p-series is you have a square root of n. So I want to remind you that when you have a square root of n, the power is actually 1/2. So anytime we have a radical, we want to change that to a power. It's going to be one of those fraction powers. And essentially, if you can recognize what it is, then we learned when we did improper integrals in chapter 8 that when we have an integral that follows this form, our integral from some value to infinity, if you have 1 over x to the p power, so that's a p-series, that series only converges when p is greater than 1. When p is less than or equal to 1, we found that that series just always diverged. And so based on that integral, and if we did the integral test on these, we'd find that the integral test would show that same result. And so the test that we're allowed to use is we're going to jump to a conclusion. And when we have a p-series, essentially all we have to do to state our test is we have to identify the value of p and say whether it converges or diverges. So here's kind of what you need to make sure you get down. It will converge, so this will converge when p is greater than 1 and diverges when p is less than or equal to 1. Now, one little thing to note is we have a special series when p is exactly 1. We call this series the harmonic series. And so you can either use the p-series test and say p equals 1, therefore the series diverges, or if you just call the series the harmonic series, you can get away with just saying that it diverges. So that's also an acceptable justification. So calling it the harmonic series or identifying p and saying that you're using the p-series test. So let's just take a look at a couple p-series and see how it works. Oops, sometimes my page gets away from me. So let's take a look at this first series. Now remember, when you have a series and you don't have a rule in front of you, the best thing you can do is to write yourself a rule. So if n is 1, we have this. So this is n is 2, 3, and 4. So this appears to be 1 over, this is 3 squared, this is 2 squared, this is 4 squared. So this appears to be 1 over n squared. So here's my p-series from n equals 1 to infinity, 1 over n squared. So p here in this case is 2. It is bigger than 1. The series converges. It's as simple as that. You don't really need to state any conditions other than saying that it's a p-series and identifying what p is. It's a pretty straightforward, very simple, very common test to have to use. So let's take a look over here. So here's my series. Now remember I said when you have a radical, you're going to want to make sure that you rewrite that radical as a power so that you can use that to, apply your p-series test. So remember, when you have, m and then you've got like a to the n, remember that the bottom of that rational exponent is your root, the top is the power. So this would be a to the n over m power. So that's how those fraction exponents work. So I'm going to rewrite this series as n equals 1 to infinity of 1 over, and then it's going to be 2/3 power. So now that I've got it in a p-series format, I'm going to identify what p is. It's 2/3. I'm going to say that it's less than 1. Therefore, the series diverges. So it's as simple and as basic as that. You might have to do a little algebra to get there. But let's keep going. Let's take a look at a couple more p-series that may not be quite so obvious. So now this p-series, you can see that it has an n and a cube root of n. So what I have to look out for is that if I have n's that are multiplied together, kind of like this, I want to find ways to use algebra to make it look like a p-series. So I'm going to remember that this is n to the 1 power and this is n to the 1/3 power. And when I add those exponents together, this is going to be n to the 4/3 power. So when I rewrite this series to make it look like a p-series, here's kind of my first step. And now here's just a little rule about p-series, or about series in general. If you have a constant, kind of the way that we've dealt with constants, I know as we've done derivatives and integrals and things like that, constants are wonderful things that we can kind of pull out and save for later. You can do the same thing with a series. So for this series, I can pull that constant out and write it like this, and then it's very obviously a p-series. And so now I'm going to say p equals 4/3, which is greater than 1, and we're going to say that the series converges. So look for ways to kind of combine your ends and make it a p-series. Doing the little algebraic maneuvering in the beginning is going to help you identify and justify whether a series converges or not. So let's take a look at one more here. So here we've got n equals 1 to infinity. We've got n squared over n cubed. And again, this doesn't look like a p-series right off the bat, but if we simplify our exponents, we get this. We get 1 over n, and oh my goodness, this is a p-series. So remember, with this particular p-series, where p equals 1, this is called the harmonic series. And so all we have to do is say, hey, this is the harmonic series, and then say that it diverges. Now, do you have to call it the harmonic series? No. Is saying p equals 1, the series diverges, enough? Absolutely. But the key is you have to identify that harmonic series or identify the p-series, say that it converges or diverges. So here are a couple of little pro tips. So as you're looking for some things, if the series is written out, determine the rule. So that first example, write down what the rule is, try to figure out what's the nth term, what's a sub n, and then use that to determine if it's a p-series. Or if it's not a p-series, what test are you going to use on it? Find ways to simplify algebraically, and it would be nice if I could spell properly. And then one last thing is if you have the harmonic series, so this is kind of like one last ending note, the harmonic series sometimes can look like this. So if I have n equals, and it really doesn't matter what I have, I'm going to start n at 2, and I'm going to have n plus 2. So this is actually the harmonic series, and it doesn't look like it right off the bat, but I can't just say necessarily that this is the harmonic series. I have to show that it's the harmonic series, and I can do that in one of two ways. I can either write out the terms and say, okay, when n is 2, this is 1/4. When n is 3, I've got 1/5 plus 1/6. I have to write out at least 3 terms and say, hey, this is the harmonic series. Or I can actually rewrite the sigma and make it the harmonic series, make it be 1 over n. And so what I can do is I can rewrite it and just pick a new starting value. And so if my series, as I'm written, starts with a 4, well then I need to make sure that when I choose a new n to start this series over, I start it with a value that's going to produce the same list of terms. So 4, 5, 6, and so on and so forth. So the terms have to match. But if you can do one of those two things, either write the terms out and show that it's the harmonic series, or rewrite it and pick a new starting value of n, then we can say that the harmonic series always diverges. So just a couple little ways to kind of get around doing some of these tests. If you can show and say that something is a harmonic series, that'll save you a little bit of time. So now you should be able to tackle any p-series and hopefully start to recognize the harmonic series so that you can determine the convergence or the divergence of those series. Nice, quick, easy test. And yeah, you've got this.